So chapter 9 is concerned with solutions. We cover all sections of this chapter except for section 9.4. So a solution is an example of a homogeneous mixture and is composed of two or more substances. There will always be one substance present in the greater amount, and we call that substance the solvent. And then there'll be one or more minor components, which we call the solutes. So if you're thinking about a cup of coffee, you probably could recognize pretty quickly that the solvent would be water. And then examples of solutes would be things like caffeine, perhaps some sweetener, the tannins, which are compounds that give tea and coffee its characteristic brown color. Because water is a very important solvent, when the solvent is water, we give it a special name. We describe the solution as being aqueous. So aqueous solutions are important because nearly all of biochemistry takes place in aqueous solution. So, for example, even in the deepest, darkest ocean where the pressure is very high and the temperature is very high, where there's complete absence of light, we'll still find biochemistry occurring. And even if we look at things like rocks that have come from Mars, when we see evidence of water, we see evidence of life. Now, this is a little bit contentious, but these structures that we see in these rocks which have been subjected to weathering by water look suspiciously like structures we would expect to be formed by microorganisms. Solutions don't have to be in the liquid state. Solutions can form between gases, and a good example of this would be the atmosphere. Solutions can form between gases and liquids. For example, we have oxygen dissolved in our blood, and there's also oxygen dissolved in water. That's why fish can breathe in water. Solutions can be between solids, and a good example of this is the class of materials called alloys, which are what are produced when we combine different metals together. So, why are some things soluble in some solvents but not soluble in others? And that's a really great question. And what we know is that solutions will form when the type of intermolecular forces between solute particles is similar to the type of intermolecular forces that can form between the solute and the solvent. For example, polar solutes will dissolve well in polar solvents because the dipole interactions between the solute particles are similar to the dipole interactions that can form between the solute and the solvent. Ionic solutes dissolve well in polar solvents because the ion-ion interactions between the particles that make up the ionic solid are similar to the dipole ion interactions that can form between the polar solvent and the ionic solute. Non-polar solutes tend to dissolve well in non-polar solvents because the dispersion forces between the solute particles are similar to the dispersion forces that will form between the non-polar solvent and the non-polar solute. So chemists often summarize this with the little phrase like dissolves like, which means polar dissolves well in polar and non-polar dissolves well in non-polar. If a liquid doesn't dissolve in a solvent, we give that liquid a particular name. We describe that liquid as being immiscible in that solvent. And a good example of that would be oil and water. If a liquid does dissolve in a given solvent, we describe that liquid as being miscible in that solvent. And a good example would be alcohol dissolved and is miscible in water. We know that alcohol is miscible in water because people sell alcoholic beverages. Okay, so that concludes section 9.1.